introduce you to the idea of integration. But it doesn't mean that you have a full, comprehensive mastery of it by any means. And that's okay, because we're going to cover it together. So antiderivatives and indefinite integrals. You saw yesterday at the very end of the Organic Chemistry Tutors Calculus in 35 Minutes the 3 basic ideas of calculus, which the AP Calculus gives us like this course guideline, basically what we're supposed to cover, and it organizes the information so that we can organize it in class. And it used to be those 3 very things: limits, derivatives, and integration. They've since kind of changed it to go away from the terms themselves and to instead incorporate the ideas. So they've adjusted it just a little bit, and I'll let you guys know that another day once we've had a little more, once we've covered a little more of what an integral is and what it does, and I'll try to give you guys those 3 topics, and then you'll kind of have a more comprehensive view of the year and of calculus itself, and we'll see if they make sense. But for right now, we'll go off of just the very basic, traditional 3 main topics of the Calculus 1 course: limits, derivatives, and integrals. So we're in that final category of integration of integrals. However, if you guys look at this entire page, there is not one integral symbol on it. There is the word integral in the title, but there's not one integral symbol. We're still building the idea a little bit. So if you notice, like yesterday, that word problem that we were given, where they said this is the rate, this is the how fast, and we want you to go to the how much, and we were going backwards. This is much more basic in that it says this is a derivative, and we want you to find the original function f of x. We could also say this is an f prime of x. You could say it that way. This is an f prime, this is a derivative, we want you to find f, but it's very similar as that word problem yesterday, but the one yesterday didn't have a prime in it. They called it the word rate, but that still indicates the same concept. Now, Kyle, how were you able to say that this was x to the 5th? As best you can, explain how you knew that.
Well, I know that in derivative rules, in the power rule, I know you take down the exponent and subtract 1. So since it's not a very high number, I know that 5 could just be the exponent, and 1 is the leading coefficient.
So it's kind of like a trial and error sort of thing, in the sense that you were like, hey, I see the 5, and I know from power rule, because this is an x to a power, that 5 could have come from being up above, so x to the 5th. And then you kind of did like a trial and error of, yeah, bring down the 5 and the 4 is left. Hey, I got it. However, if you guys look over here at the definition of antiderivative, which you wrote just a second ago, you might not have fully drawn the comparison between what's going on here. However, long story short, if you look at a function and you try to find his antiderivative, we'll explain the terminology, or I should say the notation, in just a second. We don't just say, where did you come from, who would have your derivative? We also say plus c. So we're actually going to put a little plus c. Well, actually, let's do this. I said find the function f of x given the following, but I'm going to go ahead and say find a function. Is this a function whose derivative is 5x to the 4th? Yeah. But what could I change in order to make another function whose derivative is also 5x to the 4th? Plus, make it specific. Plus
4.
8. Sure.
7.
Would that have worked?
Yes.
Yeah. How about plus 84?
Yes.
How about the square root of 841?
Yes.
What if I added a pi? Yes, because no matter what constant is here, what's going to always happen if I take the derivative of a plus constant?
0.
It's going to disappear. So the idea with this whole why do we need a plus c is because the derivative of any c alone, of any constant, is always 0. And so will we ever see a constant that was there if we're looking at the derivative? No. He will have disappeared. So we always have to kind of allow for the possibility of there having been a plus constant. So when I said find the function, well, this is not the antiderivative. If you put x to the 5th, it's an antiderivative. It's one of them. It's one possible one. But it could be plus any constant, so that's why we have this plus c thing going on over there. But before we get to the forever card, main idea, given the derivative, however, wait. I said yesterday those word problems are super important. Can we say given a rate? Can we put that in too? given a derivative, or like in a word problem, given a rate, given a how fast, a function to describe the rate, it doesn't always have a prime in it. It doesn't always have a dy dx. In a word problem, they could just say the word rate, and we have to realize it is the derivative of something. Find the original, aka differentiating backwards. The opposite of deriving, in some senses, not opposite as in negative, but opposite as in like inverse, as in going back, undoing. It's much more of an inverse relationship than an opposite relationship, speaking mathematically. But differentiating backwards. Looking at a dy dx, looking at an f prime of x, looking at a rate, and trying to go back to who was the original. Does that kind of make sense? So then if we're going backwards, if we're undoing, if we're doing that inverse relationship, maybe the word antiderivative makes sense, right? We could go into like antithesis, we could go into like heroes and villains, we could go into all sorts of yin and yang, anyway. But we can think of, we have this derivative where we're going from an original to a derivative function using all of our rules. We're thinking about finding from an amount equation a rate equation. And now we're just going the opposite direction. We're anti-deriving. We're going back. Or we're undoing a derivative. Now, this can get really confusing as in notation. And the AP loves to play with this too. And actually some teachers don't even like to show it like this because like, it makes the idea confusing. But once again, and some of the notations, for those of you that love the boxes and the triangles for product rule or quotient rule, like on the Forever quiz yesterday, if you love using like an alternate notation, that's good and that's great for you finding a derivative, but it's bad when you get to the AP and they say something like, find the derivative of f of x times g of x given all these clues, and you don't know who the functions are. You've seen it on your test and your practice test. Because you have to know the notation in order to answer those questions if they don't give you a function. So let's explain what's going on here and why there's absolutely no derivative like prime sign anywhere in here. A function, capital F? Sure, why not? We could call it anything. We could call it G, we could call it H, we could call it R for rate, like they did yesterday. Oh, wait a minute. No. Capital F is an antiderivative. Hold on. Okay, so capital F is an antiderivative. Capital F is what comes out of an integral. You guys noticed yesterday this is an integral sign, right? You need to write it somewhere, write it here. This is an integral sign. It actually is an elongated S. It actually came from the Latin for summa. Summa meaning sum, coming from summation. It's this whole thing, this whole idea of area under the curve, adding together different rectangles. We'll see that in a future section. But anyway, it's basically an elongated S, but now we just call it an integral sign. But a function f, never called an S. A function f is an antiderivative of f on an interval I if, okay, here's what you guys need to make sure that you grab. If this was on like a forever card quiz, if I was to ask you for the definition of derivative, or sorry, antiderivative, you would need to show me this right here along with this background information. So the integral of f of x dx, the integral of some anything, it could be like a capital R for rate, it could be an A for, I don't know, how fast apples are falling from a tree, it could be who knows what. But when you have a function inside an integral, that answer is called the antiderivative, but the antiderivative is defined to be the guy whose derivative is inside the integral. Okay, and I'm going to do just a little bit of vocab so that we can kind of understand and be able to start talking about these sorts of things. This little guy, the f of x, is who we're going to call the integrand if we're actually talking about the dude inside an integral. He's called the integrand if we're just looking at an integral. But if you're in like a word problem, he's just called the rate equation, whoever that guy is. And if you guys notice, there is no prime on him because the idea is you're given this. They're not telling you it's a derivative. It's just a derivative by nature of being inside an integral or being called a rate in a word problem. You're just being given some function, being like, hey, here's a function, and then you need to maybe take an integral of that, and when you do, you're looking for the original, aka the antiderivative, aka the function whose derivative is that integrand. So anyway, it might look a little bit confusing because it's like the antiderivative uses a derivative to show it or to explain it, but the reason is, depending on the context, you're not going to see him as a derivative. He's just going to be some random function that's given to you. And that random function that's given to you in context, you're going to have to realize is a rate of something, and you need to, for some reason, go back. Or you just see him in an integral and like, whatever, I just need to go back. So antiderivative is the answer to an integral equation. It's that going backwards, that anti-differentiation. We already talked about the plus c thing. And so I think this is just one further example, because usually I'd have you guys kind of ponder that original one, but Kyle came up with it pretty quickly, and some of you may have also known the answer right away. So then use the same idea for this one then. F of x is 4x cubed. They give us something. They say find the antiderivative. So don't do power rule. Go back and think where it came from. Any ideas?
X to the 4
Yeah.
plus c.
Good. If it's the antiderivative, put a plus c and say, I don't know, could be anything. If it's an antiderivative, put in a plus 2 or a minus 1 or a plus pi. Why am I saying plus c? Why not times c?
That would be different.
Why would this not work? Or divided by c?
Plus
You
0
are part of
and then
the-
times 0.
Yeah. The derivative of plus c is 0. But what's the derivative of times c? Wouldn't he be a constant in front? And so it'd be 4c x cubed?
We would see it.
Yeah. Yeah. We
Ah,
would see
see
that.
it.
Oh, we would see that c,
We
but we
see
don't.
it.
Yeah. Let's not make things more confusing than they have to be. But what if I was to give you something like, ready? The integral, just to introduce us to where we're going tomorrow. This homework's not due until Monday. What if I was to give you something like, let's do something like 7x squared. There's an integral sign, which means we have to undo a derivative. We have to go back.
Ooh,
We have to think of where this came from. Why is this not as easy?
because it's probably a fraction or something.
Why are you saying that?
Because
Because it's a 7, not a, what would you love to be there?
6.
What would you love to be there? A 3. Why would you love a 3 to be there?
Because then it's just x.
Because then it's just x cubed. Because doesn't x cubed bring down a 3 and make a 2? But what do I have instead of a 3?
7.
A 7. So wait, the 3 needs to come down, but then it goes away. What do you see, Adam?
Well, yesterday, didn't he do that thing where he did n plus 1?
There's a rule that we could memorize, but let's get the concept first. But good, that's exactly what I meant to do. Guys, to take a derivative, we could put the plus c, whatever. But to take a derivative, if I bring down the 3, if he goes away, what must have been waiting for him?
A constant.
Constant.
Right?
Yep.
If the 3 comes down, he's going to cancel out now. True. But what do I need to stay? Now, one way is you couldn't always, like with derivatives, how the derivative of 2x cubed is keep the 2, bring down the 3, and then the 2 and the 3 makes a 6x. We can actually think of the 7 outside. So we could have actually just kind of written that 7 in front and then thought about, wait, x cubed. Uh-oh, nope, I need to get rid of the... You could think of it this way. That way works too. The 7 just kind of chills and then he comes in later. But let me do another one, and then we'll see that rule that Adam was talking about yesterday, if maybe it makes sense. What if I was to give you the integral of... How about 5x to the negative 3? Still power rule. But where would this guy have come from? X to what power would have made negative 3?
K2.
Because I needed to subtract 1, right? You would have brought down, subtracted 1. Negative 2 minus 1 is negative 3. But wait, I need this negative 2 to come down and cancel. So what had to be here?
A negative.
There has to be a negative somewhere. So yeah, we could put the negative 2. But then who's chilling? Do you guys see how there's going to be a pattern every time? What is that pattern? Well, that's the rule that you saw the organic chemistry dude write yesterday, which was anytime you have an integral of an x to an n, and if you want, you could even do like a cx to the n if you want to have a constant. We can always say that my antiderivative is going to be, the c is just going to chill, like the 5 just chilled, the 7 just chilled. The c is just going to chill, but with this little x to the n part, I have to always think of adding 1 to the power because there was a 1 subtracted to get here, so I add 1 to go back. But then if you notice, I always need this division to cancel out that power. Oh no, here's a struggle. I have a plus c there, so maybe I should make this guy something like a a. We use a's in math to be constants, right? A's or k's or b's or whatever. And this would even work for the easy ones that some of you guys, well, easy, relatively speaking, that some of you guys were doing a second ago. Because if we did something like 3x squared, some of you were like, oh, that's x cubed, yay! But check it. Wouldn't it have worked if I had kept the constant and then done the x cubed all over 3? Yeah, I could follow my rule and it will work just fine. So even though some your brain just naturally will know faster than others, we can still have this rule kind of back in the back, or hopefully eventually up in the forefront of our minds. It's called the power rule for integration. Now that's just the beginning though, because wait a minute. Didn't we have a lot of derivative rules?
Yes.
So for every derivative rule, what are we thinking might be possible?
Antiderivative.
There's an antiderivative rule to go backwards. True? Except there are a few that are quite tricky, aka, well, product rule you can kind of do backwards, but it's tricky and you don't learn it until calculus BC. Quotient rule, there is never a backwards, and product rule for AB, there is never a backwards, which makes things complicated, because then that means, wait a minute, so you could have gotten derivatives that you might not be able to come back from? That's interesting. But, for right now, what's going to happen if you guys have a fraction? Now, this side looks weird to you, I realize, but for right now, I'm going to go ahead and say, guess what? If you have a dy instead of a dx, that just means you're doing this in terms of another variable. We could actually put a plus constant on that side. Long story short, you're going to have y equals. Long story short. But what would you do with a fraction? Be very, very careful. Why am I showing this to you? Because some of you might want to go play with homework. Oh, I apologize. Bye, guys. We'll get to play with integrals tomorrow. A lot more, but you have the basic idea. See you later. Finish up the graph match, and then technically you can think of homework 25 as over the weekend, but maybe a few of you can start it tonight.
Kyle can start it.